Good evening, everyone. So, I welcome you all to the problem solving session for the week 9 for the NPTEL course Fluidization Engineering. The course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. And this live session is handled by myself, Ainkara Kartiga, from the Department of Chemical Engineering, IIT Hyderabad. So, the live session runs throughout the duration of the course every Friday from 6 p.m. to 8 p.m. So this course layout we have seen in all previous weeks classes as well, but just to act as an introductory for those who are joining new for today's class, we'll implement this today. So mainly the first aspect of learning fluidization engineering is to know about the phenomenon of fluidization, what are the advantages and disadvantages of fluidized beds. So fluidization is nothing but when we are passing the fluid at a sufficiently high velocity inside the bed, the particle starts to behave like a fluid. So this is known as fluidization. So because of these properties, they have various advantages like it can have uniform heat transfer rate rather than having hot spot formation in packed beds. And also the fluidized bed, it ensures proper mixing of the particles under certain conditions, but there are certain disadvantages as well, like the corrosion of the particles, thereby leading to particle loss. So, and industrial applications of fluidized bed, it is used in various applications like catalytic reactions and biomass gasifications. So, in industry, we can find a very wide range of use for the fluidized beds. Followed by that, we also learned about the classification of solids, flow characteristics, and its outline in different types of fluidization. How we can classify solids as gel at A, B, C, and D depending on their size as well as density, and also how different solids influence the fluidization type. And the flow pattern of fluidization system, like smooth fluidization, homogeneous or heterogeneous fluidization, followed by which we saw bubbling fluidization for the gases, uh, gas solid fluidized beds, and also how these bubbles grow into slugs and we reach fast fluidization, turbulent regimes, and finally pneumatic fluidization. So we all saw how different regimes of fluidization was observed depending on the inlet fluid velocity. So, and the next one, solid movement, mixing and segregation and staging would be learned in the further classes. It has not been covered till now by the lectures. So, followed by that, we saw gas distribution system and also the various types like porous plate distributor, perforated plate distributor, nozzles and tuers type distributor, and how it is influencing the industrial scale or the small scale setups, and also how to design those distributor and how the distributor affects the pressure drop of the bed, and what are the advantages. I mean, what would be the disadvantage when we are having higher pressure drop in terms of pumping cost, etc. All these were covered in those classes. And followed by that, it was the study about the bubbling fluidized beds with special focus on gas dispersion and gas interchange in the bubbling beds and mixing characteristics that is observed inside the bubbling beds. And this is about entrainment and elucidation from fluidized beds, which was given an introduction in the last week's lectures. And this week it was completely about entrainment and elucidation with some mechanism about attrition. And followed by this, we would be dealing with attrition mechanism and its analysis by model, and also solid mixing segregation and would be studied in those classes. And last, we would be dealing with mass transfer phenomena happening inside the fluidized bed, particle to gas mass transfer, and how do we analyze this by using two-phase and three-phase models, system models, and etc. Lastly, it would be about heat transfer phenomena inside the fluidized bed and also the modeling and the design of fluidized bed reactors for physical operation, catalytic operation, or non-catalytic system. Depending on the application, the design aspects varies. So all those would be seen in the last lecture. So This course is covered by the professor through his lectures from IIT Guwahati. So this problem solving session is a aid for you people to help you or assist you in solving the assignment problems. So since we all know assignment also accounts in the final examination marks. So submitting the assignment promptly on time with proper answers is a must. So this course, this session would be helping you in solving the problems by giving some sample problems, and which would be helping you in dealing with the that week's problem. So, and in addition to that, if you people have any doubts, uh, or you need any clarification, you can always ask in the session. Mm, yeah, but one more thing is I'm noticing people are not joining the sessions in the last uh, few weeks as compared to the first weeks. So if there is anything that can be improved in this session, please let me know so that it can be improved and incorporated as well, so that it would be acting as a useful tool for you people as well. Because you people are not finding it useful at some point, you people are not joining. So if there is anything that can be improved, please let me know. Yeah. And books and references. So the first and foremost important book that needs to be read for the fluidization engineering is the Fluidization Engineering by D. Cooney and Levenspiel. This book covers almost all aspects that we need to study and understand the fluidization phenomena. So the next one is Gidaspo's Multiphase Flow and Fluidization, Continuum and Kinetic Theory Description. So this book, in addition to understanding the fluidization, it also covers aspects of modeling. In fluidization, we have two aspects. Either continuum theory to account for the solids, or the Eulerian description, wherein we track each individual particles. But in continuum theory, we assume the particles to behave as a continuum, and similar to the kinetic theory of gases, we apply kinetic theory of granular flow for the particles and assume continuum behavior for the particles. So this is given by, this aspect is explained in his book by D. Giraspo. And third one is Gibbelaro's fluidization dynamics. And fourth is Professor K Majumder's hydrodynamics and transport processes of inverse bubbly flows. So these books would assist you in understanding the in-depth concept behind the fluidization, in addition to the lecture videos available through NPTEL. So in last week class, what did we see? We saw about bubbling fluidized beds and the characteristics of bubbles. We saw few things in last week's class, like Davidson model with few assumptions, like how it is assumed as incompressible particulate phase is assumed as incompressible fluid with bulk density similar to that of a fluidized bed at minimum fluidization condition. And also we saw few assumptions, like fluidizing fluid is also assumed as incompressible fluid with constant widage epsilon mf. And in addition to that, the relative velocity between the particle and the fluid is proportional to the pressure gradient. And few other things, like bubble was assumed to be cross-sectional, circular in cross-section, and the particulate phase was assumed to be as an invisible liquid, and the pressure throughout the bubble is constant. All these were the assumptions of Davidson model 1961. So that model was a very specific one to study the bubble properties inside the fluidized bed. And also we saw the various bubbling regimes, like slow bubble regime or fast bubble regime. In slow bubble regime, the fluid moves up relative to the bubble, whereas in fast bubble regime, this fluid was moving down relative to the bubble. So with that, we saw about the pressure distribution around the bubbles, and we solved few sample problems on how to find the cloud radius. Cloud is nothing but the portion surrounding the bubble which has traces of solids in it. Since we all know the bubble carried certain amount of solids along with it, depending on the regimes of bubbling, like slow bubbling, fast bubbling, the solid circulation happens inside the bubble, or surrounding region within the bubble. Nearby the bubble. So based on that and all, we saw how to find cloud radius. And that was a sample problem. And also we saw about row and Partridge model with estimation of uh, wake fraction. Wake is nothing but the carryover of solids behind the bubble. uh, so how wake fraction is calculated, that was seen. Followed by that, it was about the bubble slugging bed regime. So in slugging regime, we saw three types: round nose slugs and flat nose slugs, and also wall slugs. Depending on how big the slugs grow in size, it was observed. And also we saw various models accounting for the slugging effect inside the bed. And yeah, so it was about last week. In this week's class lecture, it was the portion mainly covered was alliteration, entrainment, and attrition. So week 9 is all about this. So what is entrainment? In vigorously fluidized buds, if we take, the velocity of the inlet fluid is very high. So the solid particles are ejected. Consider this is the fluidized bed. When the velocity is very high, the solid particles will move from here to here to here, and there are chances for the solid particles are ejected and entrained from the dense bed. So we have dense bed till this region. Above, the chances of the solid particles to move above this region is very high. Though these particles then enter the freeboard region. Freeboard region is nothing but the between the bed surface and the gas outlet. So consider this is the gas outlet. I mean, it is a continuous zone, not two regions. So till here it is dense region. So if the particles enter this region, this is known as entrainment. This is nothing but the region between the bed surface and the gas outlet. That is known as freeboard region. These particles can then leave the freeboard and escape from the unit depending on the size of the freeboard and the velocity of the bed. As we saw, what happens is that once the particles, this is still dense region. So once the particles cross this region, this is known as freeboard region. The particle can escape from this region and escape from the unit depending on the size of the freeboard. So we need to maintain proper height of the freeboard. And also the velocity of the fluid matters. So if not, the chances of the particles escaping is very high. This results in loss of valuable materials. So it is a loss. So this is known as entrainment. Adulteration is nothing but the removal of finer particles with of some fraction. Like based on the fraction of finer materials, if we are removing it in fractions of specific size, that is known as elutriation. That is, we are removing particles of certain size range. For example, if fines are going up and they are like 600 micrometer and 100 micrometer and so on. So if I'm specifically removing 100 micrometer range of particles alone from the fluidized bed, that is known as elutriation. Like these particles are already entrained from the bed, and further entrainment of specific particles alone is known as elutriation. Attrition is nothing but when two particles come in contact and they rub against each other, and how they deal with each other is comes under attrition. So I hope this is clear. Now we'll start with this week's problem. So question 1: what is the correct unit of entrainment in the fluidized bed reactor? So what is entrainment? It is a carryover of solids. So what is the units given? Kg per meter cube per second cube, kg per meter square per second square, and option C kg per meter cube per second, or option D kg per meter square per second. Just think of the answer for a minute and then we'll discuss the answer, because since no one is willing to answer and since no one is there, we'll just think of it as a practice session. So whoever is watching this video in the future, so it would be helpful for them. So just think for a minute and then we'll discuss the answer, so that it would be improving your uh, answering abilities as well. So since it is a very straightforward question, we'll discuss the answer. So entrainment is the carryover of solids. So it is the mass that is carried by the fluid per area of cross-sectional area per unit time. So now what would be the unit? It is mass is in kg, and since it is the per unit area, so it is meter square, and it is time, so it is second. So kg per meter square second is the right answer. So option D is the right answer. Option D, kg per meter square second is the right answer. Entrainment is the carryover of particles from the fluidized bed. When the gas velocity exceeds the terminal velocity of a particle, the particle would be removed from the bed. It is the flux of solids carried out of the fluidized bed by the gas in kg per unit cross-sectional area and second. So since it is a flux, we know it is kg per meter square second. So I hope question 1 is clear to everyone. We'll move to question 2. In question 2, it is given that choose the correct option. Okay, it is like match. So option 1, it is splash zone. Option 2, it is dense bubbling phase zone. Option 3, it is lean or dispersed phase zone. So in the right hand side, it is given bulk density remains almost constant. Demarcation between bed and freeboard, and bulk density of solid decreases with height, and bulk density of solid increases with height. So what are all the options given? Option A, it is 1 for 1, Q for 1, R for 2, P for 3, or P for 1, 2, Q for 2, 3, R for 3, or Q for 1, P for 2, S for 3, and Q for 1, P for 2, 3, R for 3. So actually the right answer to this is splash zone is demarcation between bed and freeboard. So it is 1 is Q. So option A and B are removed. And option dense bubbling phase zone, in that bulk density remains almost constant, so it is P. So 2 both are P, it is right. In option 3, lean or dispersed phase zone, it is bulk density of solid decreases with height, so it is R. So option is option D. So this is the right answer. So just since I have given the answer, just think how it is and correlate it. So we'll see and express, describe this using a picture in the next slide. So till then, just since you have seen the videos, lecture videos, so it would be very simple for you guys to answer this. So yeah. Yeah, this is the fluidized bed when we are passing the fluid inside the bed at a sufficiently high velocity with the bubbling regime. We can see various zones like this. This is the dense phase zone. As we can see, the density of solid is uh, like it is uniform. More than that, it is very high. So above that we have lean phase or freeboard height. Here, as you all can see, the density is somewhat higher over here than compared to this region. Here we are seeing it to be very low. So as the height increases, the density seems to be reducing, right? But so this is lean phase or freeboard height. This is known as freeboard region, and the bottom zone is dense phase zone. So the zone between the dense phase zone and the lean phase zone, that is a small portion, is known as splash zone. This is clearly mentioned in the adjacent diagram. So this is bubbles. Here we can see uniform solids till this zone also. And from here we have this splash zone where there is high density of solids at some portion, and there is immediately above it we have low density. So there is a transition zone. We can call it transition zone. This transition zone is called as splash zone, above which the density keeps on decreasing. So from this, if we come back and look at it, we can see splash zone. It is the demarcation between the bed and the freeboard. Splash zone is Q. Dense bubbling phase zone, it is where bulk density remains almost constant. So 1 is Q, 2 is P. So answer lies between these two. And linear dispersed phase zone, as we all saw, it was bulk density of solid decreases with height. So it is R. Decreases is important. It is not increasing. So it is option D. With the last option varying, we should choose option D, not option C. So I hope now it is clear. So it is splash zone is nothing but the demarcation between bed and the freeboard, and dense bubbling phase zone is the region where bulk density remains almost constant. And in option 3 it is lean or dispersed phase zone where the bulk density of solid decreases with height. So it is matching here. Okay. So it is matching here itself. So 3 and R. So that's it. I hope you all understood this. Just look at it for once. This both the images are taken from the lecture. So we'll move on to question 2 actually. Okay, in question 2 itself there is explanation giving for the regions. So in fluidized bed we have various regions when it is bubbling. So it is explained here, the dense bubbling phase zone, as we saw the bottom region, followed by the it is the top or the lean or dispersed phase zone, and it is the freeboard section, the section of the vessel between the surface of the dense phase and the exiting gas stream from the vessel. So till the top portion it is known as a freeboard, and this freeboard allows the solids to separate from the gas stream. So when there is a carryover of solids from the dense phase zone in the freeboard region, the chances of the particles to fall back again into the bed is more. So that is the purpose of having such freeboards. And transport disengaging height, TDH, it is the freeboard height above which entrainment is constant. So I think there is a zone here. So till here we can see almost it is entrainment rate is constant, above which there is a lean, very lean region like uh, so lean phase or freeboard height is almost the same. So in above the transport disengaging height, pneumatic zone is there. Sorry, very lean phase is there where the solid particles are very less present in that zone. Whereas in the TDH, the entrainment rate is almost constant, above which the entrainment rate is very low. So those particles are carried away from the bed and they needs to be recirculated. So that is the concept. So we have dense bubbling phase, lean phase or dispersed phase with freeboard, and transport disengaging height. So that's it. In between we have splash zone. So we'll move on to question 3. In question 3 it is asked that select the correct option regarding the influence of gas density and bulk density of solid on the entrainment rate. So here it is asked to see how entrainment rate is influenced by gas density as well as the bulk density of solid. So first option it is given, entrainment rate increases with an increase in the bulk density of solid. Entrainment rate decreases with increase in bulk density of solid. Entrainment rate decreases with an increase in gas density. Both option B and C are correct. So what happens is that entrainment is the carryover of solids. If the bulk density of solid is more, the chances of the particles getting carried away is decreased. So similarly is the case where for a gas density, if the gas density is high, the carryover capacity of the gas is reduced. I hope no one is there, like because if so it is kind of difficult because I could not see them. So what happens is that the carryover capacity of the gas is reduced. I won't raise a pointer. Yeah. Carryover capacity of the gas is reduced with higher density. So entrainment rate decreases with an increase in the gas density. Similarly, entrainment rate decreases with an increase in the bulk density of solid. So answer to this is option B and C. Both option B and C are correct. So therefore the answer to this is particular question is option D. I hope I am clear. If not, just think. If you have any doubts, please ask. Your understanding improves only with more questioning. So we'll go to question 4. In question 4, it is asked that select the correct answer concerning the effect of particle size and fraction of ions on the entrainment rate. So in these questions, just be careful whether it is selecting the correct option or choosing the wrong one, because then it might go wrong with whatever options we are going to choose. So option A, it is entrainment rate marginally influenced by changing the size of coarse material. Entrainment rate is unaffected by the fraction of fines in the bed. Both option A and B are correct. Option D is none of the above. So actually the answer is both option A and B are correct, because entrainment rate is not going to change by changing the fraction of fines inside the bed. And similarly with coarser particles, when we are changing the size, the entrainment rate is marginally influenced, whereas with fines, if we are changing the fractions, it is not going to affect it. So answer is both option A and B are correct, and it is option C is the right answer. So I think it is clear. We'll go on to question 5. In question 5, it is asked that axial distribution of solid as per Lee and Quack can be expressed as epsilon s minus epsilon s star by epsilon sd minus epsilon s star is equal to exponential of minus zi into z naught. Or option B, it is epsilon s minus epsilon s star by epsilon sd minus epsilon s star is equal to exponential of minus z plus zi by z naught. Or it is epsilon s minus epsilon s star by epsilon sd minus epsilon s star is equal to exponential of minus z minus zi by z naught. Or in option D, it is epsilon s minus epsilon s star by epsilon sd minus epsilon s star is equal to exponential of z minus zi by z naught. So what happens is that axial distribution of solids is given by epsilon s minus epsilon s star by epsilon sd minus epsilon s star. So we all know that epsilon is s is a solid fraction inside the fluidized bed at that particular zone. So here epsilon sd is a value which is varies depending on the type of fluidized beds. For example, if it is bubbling bed, we have the value of epsilon sd to be 0.55 to 0.4, or else in turbulent bed we have it to be 0.4 to 0.22, or else in fast fluidization we have it to be 0.22 to 0.16. So what is epsilon s star in this? Epsilon s star is the saturation carrying capacity of the gas. That is, it can carry only certain amount of solids in it. So that amount of fraction of solids is given by epsilon s star. And epsilon sd, as we have seen, it is some type of value which is varying depending on the solid distribution. Like it is varying, epsilon sd, it is varying for the solid distribution in that particular type of bed. For example, in bubbling bed, turbulent bed, fast fluidization, the value varies within certain range. So epsilon s is the solid fraction at that instant or that position. So here we have z is the height at that instant, and zi and z naught are the bed height at specific regions corresponding to the solid fraction. I mean, Zeta and Z naught are the bed heights. So corresponding to that, we have a solid fraction profile also. So according to Lee and Quark, the axial distribution of solids is given by epsilon s minus epsilon s star, epsilon sd minus epsilon s star. Left hand side almost remains the same for all the four options. So in right hand side, what according to Lee and Quark is that exponential of minus z minus zi by z naught. Here it is into z naught, so it is wrong. Here it is given plus, so again it is wrong. So z minus zi by z naught. So option C is the right answer. And here negative sign is missed over here. So option C is the right answer. Epsilon s minus epsilon s star by epsilon sd minus epsilon s star is equal to exponential of minus of z minus zi by z naught is the right answer. So just look into the equation and try to get it. So we'll go to question 6. In question 6, it is mentioned that which of the following statement is true. Entrainment flux increases with pressure. Entrainment flux decreases with pressure. Entrainment flux is independent of pressure, none of the above. So the answer is entrainment flux increases with pressure is the right answer. So the carryover capacity is increased with pressure, that is the carrying capacity of the gas is improved with increase in pressure. Thereby the entrainment flux also increases with increase in pressure. So answer is option A is the right answer. We'll go to question 7. In question 7, okay, question 7 is a problem. The flux of solids carried out of the fluidized bed by the gas is 200 kg per meter square second. Calculate the slip velocity. So the data is solid density is given as 3000 kg per meter cube and epsilon s at the exit, that is epsilon se, is given as 0.04. So options given are US is equal to 1.67 meter per second. Option B, it is US is equal to 3.55 meter per second. Option C, it is 4.50 meter per second. Option D, it is 0.67 meter per second. Just take a minute, at least write down the formula and we will solve it after a minute. So we'll solve it. First, we'll write all the given information from this. So rho density of solids is given and solid fraction of the exit is given. So what do we need to find? Slip velocity. Slip velocity. So what is the formula? So GS is given by, sorry, exit is given by GS. So this again is given by rho S into epsilon SE into US. Rho insert epsilon insert close. So it is rho S into epsilon SE, because we are calculating it at exit, into US. So what we need to find? We need to find US, right? So what US would be, that is slip velocity, would be inverse of this, rho S into epsilon SE divided by GSE. So this is the, we know all the given values. So rho S is 3000 into epsilon SE is 0.04 divided by 200. So what is the value? 3000 into 3000 divided by 200. It is 15 into 4. So sorry, it is inverse of this. 200 divided by 3000 into 0.04. 0.04. So what actually comes is 15 into 460, 1 by 0.6, 1 divided by 0.6. So what is 1 divided by 0.6? 10 by 6, it is 1.6667 meter per second, or approximately, what was the options given? 1.67 meter per second. So answer is option A, 1.67 meter per second. So what the question, was asked in the question? In question it was asked that the flux of solids carried out of the fluidized bed by the gas is 200 kg per meter square second. So we need to calculate the slip velocity. So since it is about carrying out of the bed, GS is nothing but GSE. So it is rho S and epsilon SE are given. Density of solid and the epsilon SE at the exit is given. So it is again, so we have written first what we would do, we write all the given information and we'll then find the slip velocity. So it is, slip velocity is given by the formula, the flux rate is given by the formula GSE is equal to rho S into epsilon SE into US. So since we know all the other terms except the slip velocity US, we calculate the slip velocity US by substituting the values, and we are getting the value as 1.67 meter per second, which is the option A, So I hope it is clear now. First we write, we are asked to find the slip velocity. For that, it is flux of solids carried out of the fluidized bed is given and density of solids is given. So we input all the information and we find the slip velocity US. So we will go to question 8. In question 8, it is asked that the velocity of the gas in the fluidized bed reactor of diameter 0.7 meter is 1.5 meter per second. The fraction of the particles at the column exit is 0.06. The measured particle velocity is 0.1 meter per second. Calculate the slip velocity. So options given are US is equal to 1.5 meter per second, and it is 2.5 meters per second. Option C, it is 0.50 meter per second. Option D, it is 3.15 meter per second. So think of the question and find out the formula. We'll solve it in a minute. So we'll solve this similarly like last. We'll write the given and to find we need to find slip velocity. US. So in the given, what are all the things that are asked? Velocity of the gas in the fluidized bed reactor. So bed diameter is given. Bed diameter is 0.7 meter. So we are given gas velocity. So it is UG equal to 1.5 meter per second. Fraction of particles at the column exit. What term do we denote? We denote it by using epsilon SE, because it is exit we are using E, and because of solids we are using epsilon S. So measured particle velocity is again given 0.1 meter per second. So it is U is equal to zero point 0.1 meter per second. So we need to find the slip velocity. So this again is a very straightforward problem to be told. So this is question 8, solutions. Question 8 solution. Formulae US US is equal to U minus U U sure. So here we have one fraction that is nothing but 1 minus epsilon AC. Insert symbol epsilon close. 1 minus epsilon SE. So here we have 1.5 is the okay, it is UG actually. 1.5 divided by 1 minus 0.06 is the epsilon SC minus 0.1. So this is 1.4957 meter per second or 1.5 meter per second. So we'll look into the question again. In question 8, it is asked that the velocity of the gas in the fluidized bed reactor of diameter 0.7 meter is 1.5 meter per second. Fraction of the particles at the column exit is 0.06. Measured particle velocity is 0.1 meter per second. So calculate the slip velocity. So slip velocity is need to be known. So actually we have the option as 1.5 meter per second, which is the answer we got. So option A is the right answer. Yeah. So in given it is bed diameter is given and gas velocity is given and solid fraction at the exit is given as 0.06 meter 0.06 and the particle velocity is given as 0.1 meter per second. So we need to find the slip velocity. So slip velocity formula is US is equal to UG by 1 minus epsilon SE minus UP. So we have UG as 1.5 and divided by 1 minus 0.06 epsilon SE minus the whole term minus 0.1. So we have 1.4957 meter per second, which is approximately 1.50 meter per second on rounding off. So the correct answer to the question 8 is option A, that is 1.5 meter per second. So see the formula once and the answer once and take a short break. We'll meet again by 7:05 or yeah 7:06 or 7:05. Just take a break and come since no one has said I need a break. I'll be back. So we'll go to question 9. Choose the correct expression for a fraction of the particles at the column exit if the fine particles u is very high and epsilon s e is very low, lesser than 1. So in option 1, that is option A, it is given epsilon se is approximately equal to gs by rho s into u plus up. Option B, it is given gs by rho s into u minus up. Option C, it is rho s by gs into u minus up. Option D, none of the above. So in this question it is asked to find the fraction of particles at the column exit, that is epsilon se. If the fine particles velocity is very high and epsilon se is very lesser than 1. So answer is option B, epsilon se is approximately equal to gs by rho s u minus into u minus up. So in question 9 it is mentioned you need to find epsilon s e. So we know the formula for epsilon s e as gs by rho s into us. This us is the slip velocity and it is mentioned by u by, this is u divided by 1 minus epsilon se minus up. It is mentioned that epsilon se is very lesser than 1, lower than 1. So it becomes 1. So it becomes u minus up. Epsilon se is equal to gs by rho s into u minus up. Since it is only approximation, we are using this. So what is asked? We are asked to find the fraction of particles at the column exit. If the particle velocity is very high and the epsilon se is very lower value than 1. So how do we generally find epsilon se? Epsilon se is given by gs by rho s into us, where us is the slip velocity. This slip velocity is given by u by 1 minus epsilon se minus up. Since epsilon se is very less than 1, we are approximating it as 1 and using us is equal to u minus up. So option B is the right answer, that is gs by rho s into u minus up. This is an option given to confuse you people, option B and option C, but you can use unit analysis to find the proper one. In simpler cases, if you are confused between two options, just use unit analysis or something similar. Just use your spontaneous uh, thinking to find out the answer in case you forget the correct option. So we'll go to question 10. In question 10, it is asked that according to the freeboard entrainment model of Cooney and Levenspiel, solid distribution can be given as epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of minus a into zf. Option B, it is epsilon s minus epsilon s star by epsilon sd minus epsilon s star is equal to exponential of minus z minus zi by z naught. Epsilon, option C, it is epsilon s minus epsilon s star by epsilon sd minus epsilon s star is equal to exponential of a into zf, or none of the above. Actually in this we can eliminate one option, which is option B, because we have seen it as Lee and Quack. So according to freeboard entrainment model of Cooney and Levenspiel, solid distribution can be given by using either option A or option C in most cases. Option D in very lesser cases, because we know the answer. So it is a solid distribution, axial solid distribution in Lee and Quack model is given by option B. So for freeboard entrainment model of epsilon Cooney and Levenspiel is option A, epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of minus a into zf is the right answer. So what is Cooney and Levenspiel's model? Cooney and Levenspiel model is nothing but they introduce the freeboard entrainment model. How entrainment rate is changing with respect to height inside the fluidized bed is given by their model. For their model, they have introduced various assumptions in their model. The first one is they observed that three distinct phases is observed in the freeboard. The first phase is the gas stream with dispersed solids in them, and the second one is the agglomerates coming from the bed which is moving upward, and the third one is the agglomerates plus thin layer of solid particles which is moving down. So initially there is a gas stream which is carrying some portion of solids to the upper region, and agglomerates that is coming from the dense bed which is moving upward, and the last one is agglomerates that is coming along with a thin layer of particles which is moving downwards. So three distinct phases observed in the freeboard region according to the assumption made by the Cooney and Levenspiel for their freeboard entrainment model. The second assumption is that at any level inside the freeboard, the rate of removal of fines from the agglomerates, for example, when the agglomerate is moving upward, the fines from that agglomerate moves into the dispersed phase which is carried by the gas stream. So this rate at any level in the freeboard, the rate of removal of fines from agglomerates to form dispersed solid of phase 1 is proportional to the volume fraction of agglomerates at that level. Point to be noted is it is the volume fraction of agglomerates. And the third assumption is that the upward moving agglomerate will eventually come down, reverse its direction and move downwards. Uh, the frequency of change from this phase 2 to phase 3 is proportional to the volume fraction of phase 2. That is, we have agglomerates coming from the fines, coming with fines from the bed moving upward, and also agglomerates plus thin layer of particles which is moving downward. The moving upward is phase 2, moving downward is phase 3, which is considered in the assumption by Cooney and Levenspiel for the freeboard entrainment model. So the third assumption is that upward moving agglomerate will eventually reverse its direction and move down. The frequency of change between this phase 2, that is when it is moving upward it is phase 2 and it is moving downward it is phase 3. Frequency of change from phase 2 to phase 3 is directly proportional to the volume fraction of phase 2, that is 1 moving upward. So the answer is option A, that is epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of minus a into zf is the right answer. So we can see this is the model, entrainment model by Cooney and Levenspiel. So this is upward moving dispersed solid phase, and this is an agglomerate which is moving upward, and this is moving downward. So this is one phase, this is second phase, this is third phase. This is dense bed. So I hope this is clear. We'll go to question 11. In question 11, it is mentioned that determine the bed height at minimum fluidization. So the data given is epsilon mf is equal to 0.55, epsilon sg is equal to 0.22, epsilon se is equal to 0.05, a is equal to 1.45 meter inverse, HT is equal to 12 meter, HF is equal to 1.01 meter, epsilon S star is 0.01. Option A it is 3.25, option B it is 7.51, option D C it is 8.5, option D it is 5.66. So the question is about finding out the bed height at minimum fluidization with all the given data. We need to find the bed height at minimum fluidization, which is nothing but LMF. So four options are given. We need to find the suitable formula and apply it. This is a straightforward problem which wherein we need to substitute the given data inside a formula, and that's it. So please try to get the answer, and we'll show the results. First, we'll write all the given data. We need to find the height of the fluidized bed at minimum fluidization condition, which is given by the formula. So first we write all the given data. Given data is including minimum solid fraction at minimum fluidization condition. Sorry, void fraction at minimum fluidization condition. Solid fraction, saturation carrying capacity. Solid fraction inside the dense bed it is 0.22. Sorry, it is not, D is not dense bed, I'm sorry. Epsilon SG, we have epsilon S at the exit, and we have A, it is the decay constant 1.45 per meter. HT is 12 meter, that is the total bed height, and HF is the freeboard bed height 1.01 from, and remaining HD is the dense bed. I think epsilon SD might be density condition. Whatever. Epsilon S star is the saturation carrying capacity of the gas. Mm, so the formula is given by L minus epsilon MF is equal to epsilon SD minus epsilon SE divided by A plus HT into epsilon SD minus HF minus epsilon S star. So this is the formula which is given by LMF into 1 minus epsilon MF is equal to epsilon SD minus epsilon SE by A plus HT into epsilon SD minus HF into epsilon SD minus epsilon S star. So now this is a formula, so we'll substitute the values. Is equal, okay, okay, no, is equal to epsilon SD is 0.22 minus epsilon SE is 0.05 divided by A, which is 1.45 plus HT is 12 into epsilon SD is 0.22 minus HF is 1.01 into epsilon SD is 0.22 minus 0.01. So which is giving the values 0.1172 plus 2.64 minus 0.2121. It is again 2.5451. So how do we find LMF? Is equal to 2.5451 divided by 1 minus 0.55, which gives the value as 5.655 7 meter. This is approximately equal to 5.66 meter, which is the given answer. The answer is option D, which is 5.66 meter. So go through the question once again, and first we will go through and then you people think for a minute. So actually in question 11 it is asked to find out the minimum fluid bed height at minimum fluidization, which is nothing but LMF. So the given conditions are solid fraction at epsilon minimum fluidization condition is given, which is epsilon MF, and epsilon SD and epsilon SC, which is the carrying saturation carrying capacity of the gas, is given, and decay constant A is given, and the total bed height HT is given, and freeboard height HF is given. So we need to find LMF. So the formula to be used is given over here. This is formula LMF into 1 minus epsilon MF is equal to epsilon SD minus epsilon SE by A plus HT into epsilon SD minus HF into epsilon SD minus epsilon S star. So we know all the values except LMF. So on substituting it directly we get the answer. So go through this problem, and if you have any doubts please ask, or else we'll move to the next question. We'll go to question 12. In question 12, it is asked to calculate the freeboard height. So the data given are epsilon S star, which is 0.01, and epsilon SC, which is 0.05, and epsilon SD 0.2, and A, it is 1.8 meter inwards. So we are asked to find freeboard height HF. So option A, it is 0.2 meter. Option B, it is 1.05 meter. Option C, it is 0.87 meter. Option D, it is 0.50 meter. So yeah, we'll solve this. We need to find the freeboard height, which is nothing but HF. So the formula is, we are going to use solid distribution formula. We will insert, I think it is open, right? It is not. So the formula is given by this: epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of minus hf into a. So in this we substitute all the known things first. So epsilon se we know. So we are substituting it at epsilon s, because we know that exit solid fraction or the carryover capacity solid fraction is the same. In this instant, regarding this question, so is equal to exponential of minus 1.8 into h. On substituting this, we'll get the answer as hf is equal to okay. Maybe we can highlight it because it is missing. We'll cross check with the options given. So in the option it is 0.87 meter is the right answer. Option C is the right answer, because we are getting 0.8656, which on rounding off to 2 digits after decimal point it gives 0.87 meter. So how are we doing this? First we wrote all the given, and then we need to find HF. So we are using the solid distribution formula as epsilon s minus epsilon s star by epsilon sd minus epsilon s star, which is equal to exponential of minus a into HF. So here we know a, epsilon s is nothing but epsilon se in this problem. So we are substituting epsilon se, epsilon sd and epsilon s star, which is already given in the question. So into HF, I mean on substituting all the knowns, we, oh sorry, we are able to find HF. So HF we are obtaining as 0.87 meter. So I hope it is clear. If not, look into it and we'll discuss if you have any doubts, or we'll move to next question. We'll move on to question 13. In a fluidized bed reactor of column diameter 0.32 meter, the gas flow rate is 100 liters per minute. Calculate the superficial gas velocity in mm per second. So the options given are 5.25 mm per second, 25.50 mm per second, 10.90 mm per second, or 20.72 mm per second. Answer is 20.72 mm per second. This is a very straightforward question, so you people can answer by yourself. So just take a minute. It will be solved in less than a minute, and find out the answer. We'll solve it, however, after a minute. So since it is a very straightforward, we can solve it in a minute given to find. So what is given? Diameter of the column and flow rate. Q O is equal to 100 liters per minute. And then dia column 0.32 meter. What do we need to find? We need to find the superficial gas velocity. So it is nothing but u. How are we going to find? This one is a very straightforward problem which we have been using from the start of the course. So by now we all are very familiar with this. One liter is equal to 10 power minus 3 meter cube. So we'll just deal with in meter and then we'll substitute. 1 minute is equal to 60. So meter cube per second into, sorry, divided by 3.14 divided by 4 into 0.32. So which is nothing but 20.7297 into 10 minus 3, 10 power minus 3 meter per second. So which is nothing but 20.72 mm per second. I hope this is clear. What we have done in it is given that in a fluidized bed reactor of column diameter 0.32 meter, the gas flow rate is 100 liters per minute, which is nothing but Q. Q is 100 liters per minute. For converting, we are multiplying by 10 power minus 3 and dividing by 60 to get the unit as meter cube per second. And we need to find the superficial gas velocity USG in mm per second. So of all the options, 20.72 is matching with the one that we calculated. So how are we finding it? First we found out Q in meter cube per second, and area of the column is nothing but pi by 4 d square since it is a circular column. So we all know Q by A gives the velocity, that is superficial gas velocity. So we are dividing the flow rate by the area, cross sectional area. So that is meter cube per second and this is meter square. So on dividing it we will get meter per second, that is the unit of velocity. So U is nothing but Q by A. Q is the flow rate and A is the cross sectional area. So finally we are getting the value as 20.72 meter per second. Sorry, 20.72 into 10 power minus 3 meter per second or 20.72 mm per second, which is the one, because in the question it is asked for us to give you the answer as mm per second. I think it is clear because it is a very simple problem. Now we'll go to question 14. In question 14 it is asked that calculate the height of the column if the height of the lower dense bed is 5.4 meter and freeboard height is 1.15 meter. So again this is a straightforward question. So HT is equal to 6.55 meter, HT is equal to 12.55 meter, HT is equal to 3.25 meter, HT is equal to 9.3 meter. So it is nothing but we are having a bed. So in this still now it is dense zone. Lower dense bed height is given as 5.4. It is nothing but HD. So the freeboard height is given as HF. This is 1.15. So what is the total bed height? HT is equal to HF plus HD. So I think it will be better if we solve it. Although it is not a bigger one, for using the formula, we will solve it. So given formula. What is given? HD is given. Is given. We need to find. So the formula is nothing but HT is equal to HD plus HF. So what is HD? 5.4 and HF is 1.15. HD is 5.4 meter and it is 1.15 meter. So what is 5.4 plus 1.15? It is 6.55 meter. So the total bed height is 6.55 meter, which is given as option A. So option A is the right answer. That is height of the total bed, that is height of the column is 6.55. So it is simple question wherein we are asked to find the height of the column if the height above the height of the lower dense bed is 5.4 meter and the freeboard height is 1.15 meter. It is just a addition because we know the total column height is comprised of the lower dense region together with the freeboard height. So it is 5.4 plus 1.15, it is 6.55 meter. Option A is the right answer. So that is what we have seen in the solving approach also. This is just to give you an idea how to do it in the future or if you ever you forget the formula. So we'll move on to question 15. Select the wrong statement regarding the entrainment. Entrainment is independent of size for units larger than 0.1 meter in diameter. Entrainment flux increases with an increase in bed height. Entrainment rate decreases as superficial gas velocity increases. None of the above. In this, this is what I have meant in the earlier problem. In this, it is asked to find out the wrong statement. Previously, we were choosing which is the correct statement. So in this, we are asked to pick one wrong statement. So the first is entrainment says independent of size for units larger than 0.1 meter in diameter. This is true or false? This is a true statement because entrainment is independent of size for units larger than 0.1 meter, which above which it is not affecting. So it is independent of size. And entrainment flux increases with an increase in bed height. So particle height, that is bed height here means the packed bed height, the particle height, not the column height. So entrainment flux increases with an increase in the bed height. So if bed height increases, we all know entrainment flux increases. Option C, it is entrainment rate decreases as superficial gas velocity increases. Imagine if the velocity is increased, the carryover of the particles would be increased. It would not decrease. So this is a false statement. Option C is a false statement. Option D, none of the above. So yeah, option C here is a wrong statement. So option D doesn't work. So option C, entrainment rate decreases as the superficial gas velocity increases is the right answer. So thank you everyone for attending today's session. If you have any doubt from today's session, please feel free to ask. Or since this video is available in YouTube, you can just put out your doubts as comments. I'll be happy to answer those questions. If not, please attend the next week session. It is again the same timing from Friday 6 p.m. to 8 p.m. So at that time you can ask your questions as well. So if you want me to improve in any aspect in the class regarding teaching or regarding the problems that are chosen for your for that week, so you can always say which can be improved in the subsequent classes. So since not many people are attending, I'm not very familiar with what is going wrong. I am aware that something is going wrong somewhere, so if you give input it would be very helpful. So thank you guys, thank you. So mostly there won't be any doubt. However, we'll just wait a minute. before closing it. Thank you. Thank you. Thank you, guys. Yeah.